the schematic for the circuit that we're doing is, we've seen before, but it's basically, so I'm going to draw it in a slightly different no, I'll just draw it the standard way. Okay, so we've got plus 5 volts, right? I have 2 transistors wired in series. Okay, so these are NPNs. I've got input A, I've got input B. Those are connected to 10K resistors to the base. And then over here, I've got a 10K connected to ground. And then I've got my LED. A 330 ohm connected to ground. Okay. And then, so on the previous circuits, we had one light that was just always on that showed us that it was powered. At this point, I think we can dispense with that because, well, we know that everything's powered because stuff's happening. But we're also going to have from A and from B, we're going to put 2 LEDs each with a 330, and then we'll connect those to ground. Okay, so the benefit of doing this is we'll have 3 lights, and what we saw, the behavior we were supposed to see anyway, was that the output light, which was this one, this one, okay, was on for 1 second and off for 3, but when was it on? It was on precisely when A and B were both on. By having lights tied to A and B directly, we can actually see when A and B are on, and that'll make it visually obvious what's going on. Okay. All right. Now, in terms of the layout of the breadboard, here's how we're going to do it. Okay. So we've got our 2 rails up above. Okay. And what I'm going to do is put 5 volts here and ground there. Okay. On the same rail along the top. So 5 volts on the plus one and ground on the minus one, and put the plus one in the up direction. So we've got plus, minus. Okay. Then down at the bottom, I'm going to connect A to one of the rails and B to the other rail. Okay. And in our case, what is A and B? Where are they coming from off the Arduino? 1 and 2. Okay. So then the sort of way I'm going to lay this out is over here, I'm going to have input A, LED. And then over here, I'll have input B, LED. Okay, and then I'll have the transistors there. And then finally over here, I'll put the output LED. Okay, so that's kind of how I just want to visually allocate space for all of this on the breadboard. Is that okay? Okay, so that's sort of the big picture, and then now let's actually do it. Okay. Okay, so any questions on the schematic part of it before I switch over to actually the breadboard itself? No? Good? Okay. All right, so let me switch over to the camera and move the iPad out of the way. Okay, so here, I'll wire it to the Arduino last, okay, just for sake of keeping the desk less cluttered, well, and the breadboard. Okay, so what did we kind of decide? I'm going to put the 2 input LEDs sort of here, the transistors sort of here, and then the output LED there. Okay, All right, so let's start with the two input LEDs. So here I've got two of them, and it's probably helpful to have two different colors for this. Doesn't really make much difference though, okay? So I'm gonna have, and I'm gonna put the long edges to the left. It doesn't really matter, but if you do it always the same way, then it's consistent, okay? So I'll put the one LED, say here, and the next one, say here. Okay, good. Okay, now each LED needs what? They need to be attached to A and B. Okay, so let's do that. So A, I have down on this rail, and so I'll attach him to the positive edge of the LED. And B, I've got attached to that rail, so I'll attach him to the positive edge there. Okay, this is where they'll get their 5 volts from, basically. Okay, okay, then what else do I need? I need a resistor for each of them. So those are 330s is what I need. Right, so I need two 330 ohm resistors. Okay, and where do I need to connect those to? Yeah, the negative side of the transistor is where one of the pins on the resistor will go. And where will the other one go? Or where could the other one go? I could go straight to ground with it because notice that the legs are long enough that I can go directly from the negative side here to the ground rail. Okay. That saves me from having to throw an extra wire on here, which makes the board laid out a little bit more cleanly. Okay, so does that make sense? Yeah. And just so you're clear, right, the resistor is plugged into the negative side of the LED, not the positive side. Yeah? Okay, and do the same thing for the other one. And sometimes you kind of have to finagle the resistors, as you guys have seen. And the other thing that I've seen is problems is so don't shove them in too far because the metal that's the leads on them you've noticed is really soft. And what can happen is it can actually go inside the breadboard and like go down the row or something and cause weird shorts and stuff. So you want to get it in firmly, but not like really, really shove it all the way. Okay. Okay. So does that look good? Okay. Yes. Question. Yeah. Okay. Because remember, I've changed the layout. So where is plus 5 volts and where's ground? So where did I put plus 5? Where am I going to put plus 5 volts? On the plus. Where am I going to put ground? Up here on the minus. And then these two I'm going to use for my two inputs. So they're both going to be providing plus 5 volts, but they're going to be connected to pin 2 and 4. Okay, so this is the one thing about the breadboard, right? You see how it's labeled plus and minus down here? On this bottom rail, we're not really obeying that. Okay, so just sort of on the top rail we are, but on the bottom rail we aren't. Is that okay? Okay. Okay, so good question. Thank you. All right, so let's make sure this actually works. So what do we need to do to make sure it works? Well, I need to have ground here, plus 5 volts here. Okay, of course, nothing's going to happen. And then I've got my two inputs, so I'll put one here and one there. Okay, and if I scooch this over just a little bit, so there's two things you'll notice. You see why it was a good choice for me to put um, the plus 5 volts and the ground on the top rail and the other ones on the bottom rail? Because look at the wires coming from the Arduino. Nothing's all twisted up or anything, right? So it's organized. Okay, great success. Okay, but what do we notice if you have it wired correctly for the LEDs? What are we noticing on them? Or what should you notice? You should notice what mine are doing, which is what? Yeah, so there are four different patterns that we see, right? They both could be on, they both could be off, and then one on, one off, and there's of course two different ways of that being arranged. Okay, good. These are 10Ks. These need to be 330s.
Okay.
Yeah, 10K is way too much resistance, and so there's just not enough electricity flowing through the LED for you to actually see it.
10K. No, 10K is 330 right here.
Right, to ground. So actually, don't try and put it in the same pin as the LED. Go to, oh, and these are twisted, so they need to be like this, because otherwise you're going to have a short circuit. Right, so here and here, and then so take this one, and we'll go from there to ground, and then do the same for the other one. Okay, yeah, and then it's no, and then these are all backwards, so we need to redo this. So okay, um, so you've got here. Um, Here, let's orient it. Okay, so you have, because we redid it, right? So the plus rail here is plus 5 volts. So that's here, goes to there. Then ground, we have, previously we had put ground down there, but we're moving it here for convenience. Okay, and it'll really save our bacon later. Okay, and then pin 2 to one of those rails, and it doesn't matter which one, and pin 4 to the other.
One beside it.
Yeah, and it doesn't matter which one's pin 2 and which one's pin 4, just pick something, right? Okay. And now look at well, once you get the other resistor in, the other LED will light up. Okay, so do we all have the blinking lights in our pattern? If you do not, then please raise your hand. Um, I'm going to pause the stream real quick. So what needs to be connected to pin 2 of each transistor? Are inputs, okay? And they need to be connected via a 10K resistor. Yes? Okay. So I'm going to take my two 10K resistors, and like I did earlier with the other resistor, I'm going to go directly from the base to here, and then on this one, I'm going to go to the other rail. Okay. So those are my pin 2s, and those are going to the two different inputs, A and B, which I've got down on the bottom because we reoriented everything. 10K. Yeah. Okay, so is that all right? Now, nothing's happening differently because we're not done, right? But I've got the two bases connected, one transistor to one input, the other to the other, and it doesn't matter which order they're in, just that you have both of them, okay? It would be logical to do them in the same order as we did the LEDs, but it doesn't really matter, okay? All right, what else do these transistors need? Well, let's start with the one on the left, okay? His base we've taken care of. What does his collector need to be connected to? 5 volts, okay? And for how do I know that? Well, look back at the diagram that I drew, which I probably should have drawn it up on the board, but okay, to 5 volts, okay? So just grab a little wire, and I'm going to connect his base, or excuse me, collector, which is the left-hand pin, to 5 volts, which is up here. Okay? Good? Okay. So there's 2 of the 3. What's the third pin need to connect to? Yeah, I need to go the emitter of the first transistor to the collector of the next one. And so let me get a nice little short wire for that. So I'm going to go emitter to collector. Yeah. Okay, so let me sketch up on the board the entire diagram and then the piece of it that we've actually done. Okay, so we've got, okay, so I've got those. I've got these. I've got this wire. I've got that to plus 5 volts, and so far I have nothing else. Okay. Yeah. Okay. So and yeah, good observation. So if you look at the transistor from the front, right, it would say 2222A. It's got 3 pins: the base, the collector, and the emitter. And how do you tell which edge do you read? The flat edge. So have the flat edge facing towards you. And then base is in the middle, collectors on the left, emitters on the right for this particular kind. Okay, other transistors, guess what? The collector and the emitter flip just to keep you on your toes. Okay. Why? It's a long story. Well, because they're different types of transistors, so what collector and emitter means is different. So, yeah. Like, okay, to do this properly, I'd need a semester to like teach you guys digital electronics from the ground up, right? Um, just do that instead. Yeah, maybe. Actually, Professor Brown and I have an evil plot to do precisely that and make it like Div 101 or something, and it would be like hybridized physics and computer science with a lab. Yeah, that would be the goal, yes. Yeah. So, okay. So, what else do we need to do then? Yeah, we need to go the emitter to the LED. Okay, so let's get that in. All right, so I need another LED. So how about let's do this one. Okay, so I need my output LED, and I'm going to put him here. Okay, and it's an LED, so what does it need? Power, and it needs a 330 ohm resistor to go to ground, right? Because otherwise there's no circuit. So let me put the resistor in first. Okay, and then the power, I'm going to come from the emitter of the second transistor over to the LED. Okay, now I'm not finished. There's one other thing that I've forgotten. Okay, so let me modify or add to the diagram what we've just done. So we're not quite finished yet, though. Okay, so here I have the LED, a resistor, okay, so got that. Okay, good so far? Okay, now you'll notice that it's still a little bit dim. Yes? Or sorry, that the output LED is dim when the blue transistor is, or the blue LED is on. And the reason for that is there is a very small amount of current going from the base out the emitter, and that's enough to power the LED. It's dim, but it's powering it. Okay, so we don't want that because we have it's sort of half on, half off, if you will. Is it okay? Okay, so what's the one piece that and I forgot this, I guess it was Friday. What's the one other thing I need to add coming off the emitter of the second transistor? You guys remember? I need a 10K to ground. Okay, so let me throw that in there. Okay, so let's see. Here I've got another 10K. Yeah, for the emitter. Okay, so I need to go, so I'll put that from here, the ground, to just someplace. And then I need another small wire to connect. Here, I'm going to scooch this down. The emitter to this 10K resistor. That's not supposed to happen. You just have to. I know that's not a very satisfying answer, but so let me finagle it a little bit. All right, let me just fiddle with this for just a second here. No, same thing. Okay. Well, it basically works, right? Um, and I'll explain in a minute why basically is good enough for right now. Okay, so the salient point here is when is the output LED, and I probably have a loose wire resistor somewhere in there because that dimness shouldn't be happening. But so the salient point is when is the output LED fully on? Like, so when's really the output on? When both inputs are on, okay? And it's basically off when? When one of them is off, okay? Or when both are off. Okay, so we would say that the output is on when the input A and input B are on, okay? And in English, right, we say both, right? But A and B is true only when A and B are, oh God, that sounded really horrible. Because I just said the same thing, right? So when is the output on? When A and B are on, and it's off otherwise, okay? This is a logic gate called an AND gate. Does that make sense? Okay. Now, I can modify this circuit slightly and turn it into an OR gate. Okay, so what I'm going to do for that, you guys mind if I modify this a little bit? Okay, so let me kind of pull a few things. I'm going to leave my output LED the way it is. Okay, and I'm going to move my 10K kind of over here. And then instead of going from, let me do it this way. Instead of going, so I'm going to connect both collectors directly to 5 volts. Okay, and then both emitters, I'm going to connect one here, the other here, and then I'm going to connect both of them to the LED. Okay. All right, now observe what happens. What do you notice now? When is the output on? Whenever one or the other is on, and possibly when both are on. Yeah? Okay, so when is the red one off? When both inputs are off. Okay, let me draw the schematic of what I just changed here. So what I changed, and then this one is connected also to 5 volts. Okay, so let's think about what I've done. Okay, what was our analogy that we used last time with, like, if I've got Christmas lights, there's 2 ways that they could be wired. It could be wired one light followed immediately by another, okay? And doing so is what we did with the AND gate. That's called putting them in series. What happens if you've got a string of Christmas lights wired in series and one of them burns out? None of them will shine until you replace the broken one, okay? What about if you have them wired in parallel? If one of them goes out, well, the rest of them are fine, right? It's only that one that goes out, okay? And that's essentially what I've done here is by reorienting the transistors to be in parallel instead of in series, I've turned this thing from an and to an or, okay? Now, does it make sense that the output is on when one or the other is on? Yeah, okay. And the reason is, how can I get from plus 5 volts through the LED? Well, if this transistor is on, I can go this way. If this transistor is on, I can go that way. And if they're both on, well, I can go either way or both ways. Okay, does that make sense? Yes, question? Uh, Jiggle the resistors a little bit, and I can come look at it. But yeah, there's a reason we don't really use these kinds of transistors for much anymore, except for little stupid demonstrations like this. On Monday, we're going to start using a different kind of transistor that works on a physics principle in a different way, but also is better in many respects. And I'll explain all that Monday. Okay. But for now, let's kind of think about how many of you guys are bothered by the fact that the light is on when both inputs are on for this OR gate? Why does that bother you, Anton? It's both, okay? So the reason that maybe it bothers you is because what the word or means in English, it actually means two different things. Okay, so if I ask you guys, how many of you are in computer science class or calculus class this semester? Would you all raise your hand? Yes, because you're all sitting here in computer science class. Yeah? If I asked you, are you in computer science and calculus? Some of you would raise your hands, but not all of you, right? Okay. If you go home and you visit your parents and your mom asks, would you like apple pie or cherry pie for dessert? What would you answer? Okay, if you answer both, what's going to happen? Your mom is going to slap your ass, and you're not going to get either flavor of pie. Okay, I don't know about your moms, but my mom would, hey, you ain't having no freaking both pies. Okay, well, she wouldn't say it quite that way, but um, okay. But does it make sense though? The word or in that context meant something different. Okay, namely that having both apple and cherry was not an option. It could be one or the other, but not both. Okay. Whereas when I ask you guys, are you in math or computer science? It could be the case that you're in both. That's perfectly fine, right? You're not going to get slapped by your mother for that. Okay. Well, maybe you will. I don't know. Okay. So do you guys see the distinction between the two senses of the word or? Okay. So in logic or in, well, electronics, what we call these two different senses inclusive or an exclusive or. Inclusive or would be like, are you in computer science or calculus? Both things being true is perfectly fine. Exclusive or, it can be one or the other, but not both. Okay, so that would be the pi example. And sometimes we'll abbreviate these, this one either EOR or IOR, or sorry, yeah, and then this one often we use X for exclusive, okay? Um, so in logic or mathematical cases, sometimes we'll actually use the word XOR instead of the English word or to make it clear which one we mean. Okay, there are also circuit symbols for these, and we'll talk about that next week. Okay, so does that kind of make sense? Okay, so let's just kind of review slightly what we've done, okay, and then we'll start talking about where we're going to go with this on Monday. Okay, so we've, hopefully by this point, have an AND gate, and by making the modifications I just did, we've turned it into an OR gate. So we can see that with AND, okay, so this is, by the way, an inclusive OR gate because both of them being on, the output is still on. Okay, so this is not our pi example. Later, we will actually build an exclusive OR gate, but I think it's going to surprise you guys that it's going to take, let me count, 12, 16 transistors to do it. Okay. Okay, which is going to be a very complicated circuit. Now, we're not going to build that circuit all at once. We're going to build it up in stages. Okay, that will become a little bit more clear later how we'll do that. Okay, so let's talk about the other kind of transistors that we're going to use. So this kind, the NPN, which is what we've used in our circuits here, there's also a PNP, which I mentioned. We haven't used it, and we probably won't. Those are BJTs, bipolar junction transistors. They're current controlled. I apply a current to the base, so there's actually electrons flowing, and things happen. The other kind of another kind of transistor that we're going to use are called MOSFETs. Okay, so MOSFET, let me just write it up here, stands for, and say this 5 times fast, metal oxide semiconductor field effect transistor. Okay, I can, yes. Metal oxide semiconductor field effect transistor. MOSFET. Okay, so yes, say that 5 times over while hopping on one foot, rubbing your tummy, patting your head, right? So let's see if I can do it. Metal oxide semiconductor field effect transistor. 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 Okay. Yeah. Okay. Okay, don't, however, try to say that word and consume an alcoholic beverage in the same 24-hour period. Okay, okay. Okay, so the name actually gives away what they are. They are field effect transistors rather than being bipolar junction transistors. They work using a different kind of physics. Okay, and what's nice about these is they're not current controlled, but rather voltage controlled. So you can have voltage without any current flowing, because what is voltage fundamentally? It's electrical potential. That doesn't mean that there's actually current flowing. There's just the potential of it flowing. Okay, a good way to make an analogy here would be this stapler has potential energy, right? But is there any change in energy right now? No, because it's stationary. If I drop it, what happens? Some of that potential energy gets converted to kinetic energy by virtue of gravity. Okay, and so maybe another way to say this in an electrical sense is imagine I'm holding a 9-volt battery in my hand. There is an electrical potential, 9 volts. Is there any current flowing? Not unless I plug something in or touch it to the tip of my tongue or something, right? Um, yeah, I wouldn't recommend leaving it there, but if you just do it real quickly, you can test them, right? Um, okay, so the benefit of this, so you guys remember when I had the AND gate and that output LED was a little dim, right? That problem will basically disappear with the field effect transistors, okay? However, so if we go back to, well, we'll talk about this more Monday, but the brilliance of how to use field effect transistors is actually to put them in matching pairs or complementary pairs, okay? And this gives us the word CMOS, which is complementary metal oxide semiconductor. So every time we have, so if you look in the baggies, you'll see that there are 2 different field effect transistors. There's the N-type and the P-type. Okay, so every circuit we're going to build starting next week is going to have an even number of transistors, because for every PFET, there's going to be a complementary INFET, and the pattern for this is actually really beautiful, and I think you guys will like it. Okay, well, once you see it, it'll take a few minutes to build up to it. Okay, so quick question. how many of you guys have taken like the logic, symbolic logic class in the philosophy department? So you are, okay. Have you guys talked about De Morgan's laws yet? Okay. Has anybody else taken that class? Or what about Math 108? Well, okay. You took Math 108? No, that's not the question I asked. Yeah, yeah, that's very obvious. Okay. Love you, JoJo. Okay, so go ahead and put everything back, and you can leave your circuits plugged in. Don't worry about disconnecting, and we'll start with the field effect transistors on Monday. Okay. All right. Have a great weekend.